Yeah, I'm going to change topic a bit. Okay. I'm proud to give the first lecture in the T-shirt. So I will switch gear a little bit. So change a little bit the topic for this third lecture, and I'd like to discuss something that could be called the benefit of overparametrization in statistical learning. But in a sense, what I'm going to try to do is to sort of give you a roadmap. So it's in a way, leading to more questions that I'm going to give you answers. But it's a roadmap to try to understand why deep learning performs as well as it does. So in the previous lectures, there's been mention of these mysteries of deep learning, which is why is it that we can throw this very usually over-parameterized model to learn certain things, that we can actually learn them, that there is no overfitting, and that they generalize well outside of the data set, even though they are trained on something that in principle is fairly sparse. Okay? And so what I'd like to do is to show you that maybe there's a way to think about these problems, which in fact is somewhat closely connected, even though different from the viewpoint of the NTK. Okay, and I'll get to the NTK by the end of the lecture, which is just essentially a few lines about the NTK from the perspective that I'm going to tell you about. Okay, so the setup will be like this, just to kind of think a little bit about the issue. Right, we assume that we have a parametric model. So parametric model, I'll describe it as being phi of theta, and the parameters are these theta, which lives into some space. Okay, and what we would like to do is that we would like to fit this model. Think this could be a function, for example. That's the case that we know it could be a function that this could be a neural network, for example. You give it an input and it gives you an output, like in the context of regression or classification, classifier or a function. Okay, and so you want to or to fit this parametric model is that, well, you have a loss. I'll write it. You introduce an R of phi of theta, which is in general something which is like a convex function of this phi. Which then you think about as being a loss in the parameter theta, right? And then, well, the aim is to try to minimize. You want to minimize this guy to find, you want to minimize this over theta. And typically, if you do machine learning, the way you do that, and I'll just write it. Well, we can write it like that, but I'm going to use a continuous version of that. Is you would do something which is you just compute the grade of the loss at the current value of the theta, and you do gradient descent or stochastic gradient descent. Okay. So the mystery here is that the biggest problem is that typically this model here is such that the parameter, if it's a neural network, enter this in a nonlinear way. And so what happened is that this loss here that was convex in phi is no longer convex in theta. And so if you try to optimize that by gradient descent, it's absolutely not clear at all why this would converge. Okay. There is another issue that you can think about, that typically you write a risk here, but you don't have access to this risk. Typically what you have access to is an empirical version of the risk. And so what you're learning is, even if you are able to learn it, has statistical error that's associated with it because your data was incomplete. And so it's not completely clear how the minimizer that you will get on the empirical risk will perform on the population risk. That's the generalization error, right? And then there is something else, which is that in the standard, if you do standard statistical learning, you might be interested in finding the parameters, meaning that there is a target I'll call it later, there's an F star which is your target model, and this guy is in fact something like this, and you'd like to find what this theta star is, right? But it could be that you're not in this class. For a neural network, it's not completely clear. I mean, it's not clear that you have a planted model, which would be that, right? And so it could be that, this model, in fact, this parametric model that you have could be too small, in fact, to represent the F star. So it's a question of approximation error. Okay? So what I'd like to show you that there is a way to maybe address all of these issues in a way. The one of the approximation error, the convexity of the loss, the convergence of the gradient descent by changing the problem a little bit. Not a little bit, actually, modifying it. That's what I'm going to be describing, which is this mean field limit. And what I'm going to be discussing here is really something that there was a series of paper in 2018 by Grant Rotzkopf and myself, but also by Spiliopoulos and Song Mei and Andrea Montanari and other authors, and then Bach and Shiza, and this is part of this story. But the way I'm going to, and you have heard about it probably from Andrea, part of it, but I'll give you another take on it. Okay? So let's imagine, so to fix ideas, right, I'll assume that, so I'll make that in red maybe, that this takes, value in some Hilbert space, okay? And I'll denote the scalar product in this space simply like that. If it's, and the norm just like this. So this is in this Hilbert space. And to fix ideas, what we're going to take as a risk, so the risk, I'll write it here, we'll assume that there is some target function here which is also lives in this space, right? And as a risk, I'll just take the square. You can generalize that, but right, like that. I'm going to take this as being the risk that I want to have. So it's just, the square of this. Okay? So for example, right, you could imagine that this is a neural network, right? And you have some data that is available. And so let me write it here. You could think about the risk as being the empirical risk that you put on your phi of theta will be the integral, over some data set, d nu x, of the phi of theta evaluated at x minus your f star of x squared. Okay? And correspondingly, you could imagine that the empirical risk with whom you will actually work will be this, just to fix ideas. Okay, where in this case the xi would be independent sample from this data. So this is the data distribution. And I'm assuming that there's a target function that I'd like to, so it's like regression or classification. So you can think about this even though, and I'm going to focus on this even though at the end of the day what I'm going to discuss is a little bit more general. Okay, so that's what we're going to do. Okay, so, and as I say, you could think about this guy here as being a neural network or a deep neural network, if you wish, already. Right, where theta is all the parameters that you have in this network. Okay? Okay, so the idea of this mean field limit or this overparameterization is to say, well, let's change the problem. Instead of looking at this, whatever was your statistical model, okay, I want to look at a different problem where I'm going to introduce a new model, which I'm going to call FM for time being, which is just this. Where each of the theta I, so now I've introduced two parameters, and you'll see why I need both in a minute. are in R or in R plus. So what I'm doing here is essentially you take whatever models you had at the beginning. Imagine you have your neural network, for example, and you just decide that instead of using that guy, you make it wider and you superpose them. That's this. Okay, everybody understand what that is? It's just like, okay. So clearly, if you want to do if the aim of the game, which is in fact typically what more standard or classical statistical learning, would be the parameters that you want to, the parameter here have value in themselves. They could be like, I don't know, the cosmological constant in your model of the universe. You'd like to identify them, right? If that's your aim, this is a bad idea. Because at the end of the day, we will see there is little information about the parameters that we're going to get. And it could be that if we train the model twice, we're going to get different sets of parameters, right? So in terms of model identification, this strategy is not that useful. However, if I think about a neural network as being a black box where you need to, what you at the end want to do is to train it in such a way that it performs a function, that's a good idea in the sense that the classifier that you're going to get or the function that you're going to get will perform well, even if you don't know what the parameters are. You have no control on the parameters. Okay? If you want to make an analogy, maybe a lousy analogy with the brain, is that the way I'm becoming friend with you is by, is not by looking at the way your brain is wired, but more as an input-output. What's happening in there, I don't really care. Okay, it's just. Right. So why is this useful to think about it this way? So I'll try to explain why that's useful from the viewpoint of approximation, then from the viewpoint of dynamics, which is optimization, and eventually, time permitting, from the viewpoint of generalization. Okay? Yeah.
So here you assume that you have some fixed theta i's and you are just somehow have a basis in the...
No. I'm going to optimize what we're going to do. So what we're going to do here, just looking ahead, is that I'm going to replace this loss here, which was the loss for 1 theta, right? So we're going to, in this, so I can write it already here, but we'll get to that in a minute. I'm going to have a new loss, which is this loss, which is of all the parameters in the model, and I'm going to minimize that. Right? The aim will be to minimize this.
So do you think mostly of CIs as non-negative or and maybe a mean one, so that you have like basically a convex combination of the...
Not necessarily. So let me get to that now. You can...
It means that if you can solve this, you can solve also the simpler problem with only one parameter, right?
That's right, but bear with me for a second. I mean, that's not right actually, because this is a larger space of learning. But you're right. You could say, well, if it was a planted model, why do I bother to do that? And if you bear with me a little bit, you'll see why. That in fact it's easier to learn this way, okay, and maybe then prune at the end your network than to try to go directly at that level. Okay. So let me explain that now. Okay, first of all, and there is a scaling that I have put here, which is kind of important, and that's going to be mean field. Okay, and if I get to it, later on, we're going to do NTK, where we're going to replace that by 1 over square root of m. But this is like for later in the class. Right? It's just to looking ahead. For the moment, we're going to do this. So why is this useful? Well, it's useful because of, in some sense, elementary probability, which is that if I allow myself to look at the class of this function, where I can take m as large as I want, okay, you see that what I can represent here are functions which are in this class, actually. So where I take a measure which is on both C and theta. So this is equal. This is a probability measure. Right? And clearly you can think, if I give you any probability measure here, right? You can think about this as an atomic approximation with m atoms of this expectation. Okay? Okay, I'll do one more thing here, which is that clearly you see, and this is why I will need to play with the C. You'll see why they are important at the end. I can do an integration here over C and rewrite that also simply like this. Well, now this is a radon measure. So what is a radon measure? Well, it's a measure that doesn't need to be neither normalized nor with a definite sign. Okay? And in some sense, this weighted sum is a way to approach a radon measure. Okay? Now, notice immediately something which will be kind of interesting, is that so what we're gonna do essentially is to think about, instead of thinking about the optimization over this parameter here, we'll essentially think about the optimization over this measure. Right? By saying at the end of the day, if I take enough of these guys, in practice what I'm doing is optimizing over the measure here. Okay? Or equivalently over the radon measure there. Right? And there is something that is interesting, which is that in my new, because if I assume that this was convex, I mean, it's certainly the case here, right? You see that, in fact, I have replaced that, right, by something which is, let's just write it down. I mean, actually, let me write it just with the norm, right? The norm notation that I used here, right? Okay, I can write it here. I have replaced this by either in terms of gamma, or in terms of, you can think in terms of gamma or in terms of mu, but I have replaced this object by this. And this here, right, was non-convex in the theta, but this one is convex in the gamma, right? Here, theta is what I'm optimizing upon. At this level, the quantity that I need to optimize upon when I think about in this term is gamma. This is just a dummy integration variable, right? This is it's a d of gamma, theta, sorry, gamma of theta. Okay? Okay, so let's think a little bit about this. First, so now I need to explain a few things, so I'll erase. You remember this. For a while, it won't make any difference if we think about this or about that. It's just a change of norm in a way. Right? The only difference will happen at the end, that if I do the optimization at that level, I will need to ask myself what happened if I use this risk. But for time being, I can just think about, abstractly, this is one of these two norms. So I'm either working in the data set or the full space of the data. Okay, so let's think. So function that can be represented in this class form a Banach space. Okay, so I can think about all the function, right, that I can represent this way. Okay, and think about what is the class of this function. How does it compare with H here? The original, the Hilbert space I'm starting from. Okay, the L2 in this case, L2 of X nu. Okay, so I can. The first question I can ask is that, right? And okay, so this is clearly function in this class are a subset of H, but I'm claiming it's a Banach space. That means that I can actually introduce a norm, right? So let's just so it's a Banach space. So I can introduce a norm. It's not an Hilbert space, it's a Banach space. So let's try to think about, and the aim of the class also is to show you that you can recover certain things that you have already seen in a more general setup, in fact, by using a simple tool from probability. Okay, so I'm going to introduce a norm in this Banach space, which is, right, which will go essentially like this. Suppose I look at the difference between f and fm at finite m, right? So this guy, I'm going a little bit too fast. There is a first statement that you can make, which is that if the ci and the theta I are drawn from mu, right? Imagine that I have a function in this class. Then I can represent it by drawing independently c's and theta from this measure mu and using this sum as an approximation, right? The law of large number tells me that as m goes to infinity, this will converge to that function. Now I can ask myself, how large does m needs to be to observe convergence? And so to do that, what do you do? Well, you go to the CLT, okay? What does the CLT does? Well, it tells you that the discrepancy between these two at finite m, if you scale it by 1 over square root of, scale like 1 over square root of m times a Gaussian random variable, right? And this Gaussian random variable, you can actually compute what is its variance or covariance fairly easily, right? Or equivalently, you can think about what's going to happen if I look at the discrepancy in the loss here. Meaning if I look at how this will scale, fm minus f square, in this h, okay? Where you would take the expectation with respect to the parameters, right? So if you do this calculation and you assume that the parameters here are drawn independently, there's a little ... you're going to get into something that you need to calculate, which is just the second moment, right? When you expand this guy, okay? So if I'm going to take the expectation here, right? What you're going to get is these calculations are very standard. You get, the fm square, and then fmf, and then the f square, and then in the fm square it's a double sum, right? And then in the double sum there is one part that is peculiar, which is the term where the diagonal on the double sum, right? And that gives you, in fact, the second moment in the variance that control the size of the error. So I'm just going to write what that object is, right? This is the ... What you end up having is this guy. Everybody, so this will scale like that 1 over m. Okay? So what's the space that I can take now, right? This Banach space, so let's call it F, is the space of all function f that I can represent like this, and which are such that this is less than infinity. Okay? In general, this representation may not be unique, so what you can do here is you can take an inf over this object, where you take the inf over all measure mu, which are such that this equality is still satisfied. Right? You look at all possible representation of this function by mu, it could be more than one, right? And then you minimize this norm. Okay? So now you have a Banach space with this norm. This norm, in fact, is something that you have encountered in certain cases, because if you assume that, let me write it here. I'll write it in color so that we don't. If you assume that phi of theta square h is less than k, say, that this guy is bounded, right? Well, you can bound the object which is here by the integral of c squared d mu, simply with a k, okay? And then when you look, there is the inf over all mu, you can make this guy atomic here on the c's So this is like, this has become like a second moment that you are calculating for every theta, right? And in fact, this guy, when you take the inf, is simply k times the integral of the. So this is the TV norm of the underlying measure gamma, which is defined. It's when you integrate this, you get the guy that's there.
Where's the square go?
That is in with a square. Sorry.
Okay.
Right? That's essentially because what you can do here is that you can put all the mass on a C that's one value of C positive, the same value negative. Okay? And then it essentially disappears there, and if you use the Jordan decomposition of this radon measure, you will see that you can have equality between these two things.
Can we go through it? Because I thought if I discretize the integral with the C squared, then mu, I get the sum of Ci squared.
Yes.
But I thought that the norm, TV norm squared is instead sum of absolute value of Ci all squared. So
That's right. But if they are the same, if all the C's are the same, this is the same.
So how
What?
can you ensure, like, so I'm not sure, like, if F can be, maybe F does not have a representation where all the CIs are the same. How can you make
No,
it?
you can always do that. You can always do that, right? Because at the end of the day, that's why, I mean, you can always, among all of these classes, you can always take the one. You only need to specify, at the end of the day here, you only need to specify this radon measure, right? And then you simply need to lift this radon measure into a probability measure, okay? And so it's a 1-1, so you can, instead of thinking about this way, you could have said the representation I have is with a radon measure like that, and then you can lift the radon measure this way, and there is one way to lift, which is using what's called the Jordan decomposition of this measure, which essentially says that this guy is a sum of two probability measure in theta, right? And Dirac and C are two values of C which are positive and negative at the same constant. Okay? Okay. So that, I mean, let me not do that calculation because I'm going to take too much time, but that's essentially it. Notice that you don't necessarily have to do this, and you could work in this space in which the H here, right, this norm contains the data distribution in it, right? So this is actually a norm which is, in some sense, is not very practical because it may be difficult to calculate it exactly because you have only partial access over the data distribution, but it's more informative a priori, particularly if your data is concentrated on small set in H, but typically this guy here, this upper bound here, will be way worse than what that was. Okay? And the smaller the norm, the larger the space, as you know. Okay? So you have already this. You know that you're going to learn into this space, and then you can work a little bit harder, and you can show a statement, and this is in the paper with Grant. In fact, it's a variant of this universal approximation theorem that says that if the scalar product of if you look at this scalar product in H, if this being equal to 0 implies, so this is now a function of theta, right? If this function implies that G is equal to 0, but not necessarily the reverse, right? This condition, which is in fact saying, if you wish, that your model is discriminatory, this alone guarantees that F is a dense subspace in H. Okay? So with respect to the question that was asked before, this says that in fact you gain quite a lot by doing this with respect to the original representation, since in the original representation the only thing you could represent our function which is in this class, planted, right? And so, you know, that's a very small subset of that space, whereas this one, provided that you have this condition here, is now a dense subspace of H. Okay. So these are kind of preliminaries, right? Which just tell you that, well, I can define a space, I can define something that controls the approximation error. In fact, it is this norm. We will go back to it when you do generalization. It's also something that if you want to control the generalization error, just looking ahead, that's the norm that you should control. Okay, that's the way you should regularize to control the norm is the data if you are working with a finite data set instead of the population loss.
I'm a bit confused. How can it be not an if and only if? How can the constant zero function have anything other than a zero dot product?
This one?
Yes.
Well, you could, I mean, you can, if you take polynomials, for example, you will see that this condition is not satisfied, right?
No,
You
the
can see-
condition might not be satisfied. That I understand. No, but I just want to understand. Ah, okay. Okay.
Yeah.
So it is an if and only if G equals 0, the condition means that G equals 0.
If you pick a G and this condition is, this is 0 for all theta,
Yes.
this needs to guarantee that G is actually equal to 0.
Yes. Okay.
Okay? That's what guarantees, that's the discriminatory aspect of the unit, and that's what guarantees that the space is dense. Okay? Okay. So maybe this is a little bit of, kind of functional analytic abstract nonsense, but we can do a bit more than that, which is that now we can, so this is, so again, this is saying I can, by this picture, you can enlarge the space in which you learn,
I think
and you can, right?
This is like boosting in machine learning.
It-
Saying that if the space, you can always find a weak learner, a weak discriminator, then you can boost it up by a linear combination of them and get a high.
Okay, that's maybe that's okay. So I don't. I'm not sure. I'm not sure. I say that, this is something that you might know and I might not know.
What? You're saying that the condition that there is always a positive dot product, there is always some theta I that gives you a positive dot product, means that there is a weak learner in the class, and then you boost it into a strong learner.
Okay, maybe the discuss. So now let me look at what's happening with the, So I have discussed briefly what happened in terms of approximation, which is the space, etc., which is useful to to calculate some error. Now I want to think a little bit about what's happening with this statement, right? Which is the fact that in this original representation, the loss is not convex, so I don't exactly know what's going on with this. Okay, and now I want to try to understand whether I can make stronger statements if I now do the same gradient descent, but the gradient descent that I do is with respect to the loss that is there. So what we're going to do, right, is that, and let me rewrite it here, we're going to, we think about this object, which is, so let's write it completely, right? I need the 1/2 just so it's 1 over m. So it's the Fm. I'm just writing it. I'm thinking about this loss, and I'm going to do gradient descent on the loss. Okay? And so I'm going to allow me to write down this equation in continuous time because it's easier for the analysis. Right? And so I'm going to introduce a dynamic here, and the dynamic will be, so what I want to have is that, I'm going to get Ci and then theta I dot, and this one will be minus the gradient with respect to Ci of this big L. Maybe I could put a little at on it to distinguish it from the one that was there. And then here I'm going to do d theta I of L. And in order to have a dynamics that's actually non-trivial, you need to scale this by m, which is the same m that appeared there. Because if you do that, I can let you do this little calculation by yourself. What you obtain is that this equation becomes simply minus, so I'll write it like that, Fm, So Fm is always this, so you need to think about it, right? I'm going to use this shorthand notation, which is this guy here is Fm, as well written there, minus F star phi of theta I. That's one dynamical equation that you get, and then where this is the scalar product in H, and then the other one is Ci d theta of phi I. You know, it's a square, so this is the, and then you have the product where you just take the derivative with respect to that. So these are the equations now that you would have to implement, okay? And as you can see, they are different from the one that were here, because since Fm contained the whole sum here, you're coupling all of these parameters together, right? Okay. And so now, I mean, clearly, right, we already see from here that, in fact, in this representation, the label of this, so these parameters here, right, are indistinguishable. I can, you know, I can relabel them the way I want without changing the representation, which means, in fact, that all of the information that I need about them is contained into what's called the empirical distribution. So let me introduce that. Okay, so I'm going to introduce a mu m, which will be a mu m of t, which is a measure in dc and d theta, which is simply obtained as being 1 over m, the sum from I equal 1 up to m. So it's the empirical measure where you put a point mass in C at Ci and a point mass in theta at theta I. Right? The reason why this is useful is because you can see that I can now represent the function f as being an expectation with respect to this empirical measure. This is just right? That's what the Dirac tell you. Okay? Yeah.
Just one thing. Why does this scale by m?
Because when you do the derivative, if you don't scale by m, you'd get a 1 over m and a 1 over m. And I will want, eventually I'll take the limit as m goes to infinity. And so this is the dynamics, which is where the dynamics occur on a time scale where it doesn't depend on m. Okay? Otherwise, it would slow down as you increase m. So that's the natural time scale, if you wish. Right? And
This is the derivative with respect to theta I in the second equation?
yeah, this is the derivative of, so shorthand notation is the gradient with respect to theta of this guy,
Yes.
right? Evaluate at theta I. Okay, so if you want, I mean, I could double the index like that, but it's just the gradient of that guy with respect to theta. Okay? Okay, so now, I mean, what's interesting is that you can use chain rule to write down an equation for this mu m. So let me maybe try to do that to see. So suppose I take a test function. Let's call it phi. So I take a test function, and I evaluate it along the Ci. I'm going to write the time one time, and then I'll go here. So I take this is a test function, and I evaluate it along the trajectory that's given here. Okay. So this guy is you see by definition I can represent as being the integral of this phi. It's another variant of the one that is above, where I can I have this quantity dc d theta. Okay, and now of course at this level so I'll write it simply here. This guy depends on time because these guys depend on time. Right. So now what I can do is I can take d over dt of this, right? And well, there is no time dependency here. These are dummy variables. So what I end up having is that I get a d over dt there. Yes? But then, well, I can simply use that's the chain rule part. This is 1 over m, the sum from I equal 1 up to m of the derivative with respect to c of phi evaluated at ci of t, theta I of t, times c dot, but c dot is this. So let's put a minus, right? I'm going to write it with a big bracket here. So I have fm minus f star that's simply using the fact that this guy here is ci dot, and I've used the equation that's there. And perhaps Andrea did this calculation, and then I could actually go faster. But there's another term here which is plus, the d theta of phi, the test function again at cit, theta it, and now it's multiplied by theta dot. So I can put, there's a ci here which was this one, and then I can write it the way okay, maybe it's clear if I put it over on this side. And then it's fm minus f star, the gradient with respect to theta of theta I h. Okay? You have this, right? Now, you realize that I can replace all of this by minus the integral of dc of phi of c theta fm minus f star sorry, it's a bit long, but we're going to get there. All of this on this mu tm dc d theta. Again, using the definition of what this guy is. Right? And the final little piece of observation is that fm, that's the line here, is in fact itself expressed as something that involves mu m. So what does that mean? This means that if I look at what is, if I look at this, this guy, and I equate it with, the equality is here, with what is in this big box, make a big box, right? You see that what you have obtained is a closed equation, evolution equation for mu m, right? Is that, I'm going to write it, it's written in weak form, as it should, because this is only just a distribution, right? But I'm gonna write it in strong form because it's easier, right? It says that for every test function, the evolution of this measure satisfies this equation. Okay? So let me write it maybe, where shall I write? I'll write it here because we'll need it. I'll write the equation here. So it says dt of this mu m of t is equal to, right? And now if you integrate this thing by part, what you end up having is, okay, so let me, right, is dc, there was a minus that disappeared because I do the integration by part, and then it's fm minus f star times phi of theta in h, and then I have my mu m. So these are mu. So no, this depends on time. This depends on time. This depends on time because it's a function of mu m. Right? I have this guy plus the d theta this is the equation that I've obtained. Yes?
Can I interpret this the just written equation is the transport for the measure?
Exactly.
And the gradient flow equations are inside the equation for the flow?
Yes.
It's the same spirit of the previous two lectures.
Yes. So well, yes. This is a Vlasov equation. It's just a transport for the measure. It's different from maybe what we did last time, because here it's a nonlinear equation, because this guy is a function of, right? What I'm talking about here is that I'm using this guy where they all depend on time. And so it's a nonlinear equation because you have the measure that appears here in there. In fact, in a minute, we're going to make a connection with the NTK, and you'll see that that's the main difference with the NTK. Okay? Yes?
If you did this in discrete time, how much would it change? And like the stability in that problem?
I mean, you can do it, but it's, as usual, much more tedious, because then, you can't use chain rule, right? You need to do an expansion, then you need to control all the remaining. This is, in continuous time, what I've written here is an inequality. In discrete time, you would need, to use, as Michael Jordan was doing, you need to use the dynamics inside here, then you need to expand, then you need to control terms, etc., etc. Right? So let's not go there for time being. I want to continue. Yeah.
Using a C maybe instead of dictator.
That's right, which I can put there. And in a minute, we will see why this C, that's coming now, why I'm dragging this C all over. That the representation was not just a superposition like that, but I introduced this. Okay? That was already important for the representation quality of the, from the space that I defined, but you'll see in a minute that it's more important at this level. So is everyone happy with this? Okay, so now, the title of the paper with Grant was, by the way, parameters as particles, because these are the parameters in my extended, right, superposed neural network. But if you think as a physicist, you can really think about this as being, particles that are evolved and interact. It's a system of interacting particles, and they're interacting because the FM coupled them all together. Okay, and so you can look at what's happening. So now there's a statement that you can make, which is that let's assume that. So I didn't specify the initial condition for this equation. But let's assume that I solve this equation with, so maybe I have enough space to write them here, with a C I at time 0 and a mu I at time, and a theta I at time 0, that I draw from a certain, measure dc d theta, right? And assume that I do that independently, okay? And assume in addition that this guy is in fact not a singular measure. So for example, you could imagine that, let's imagine that this has a density, for example. So it's a PDF. So I could actually write that, as being a certain rho 0 of c theta dc d theta. Okay, let's imagine that I take initial condition this way. So imagine that there's a density with respect to, so the DC, which is in R, let's imagine that theta lives again on the torus or whatever, or in the compact space. This is just the Hausdorff measure on that space. So I assume that there is a density. Okay. If you do that, then you can build on a lot of results. And as I say, I'm not claiming that I'm proving all of the statements I'm making here. I'm giving you a roadmap, but you can build on many statements from interacting particle systems that tells you that in the limit if you look at, if the limit as m goes to infinity, this measure mu m of t converges weakly, so in the sense of measure, towards a measure mu t, and mu t satisfies exactly the same equation, except that in this equation, the initial condition was just this singular nightmare here, right? The sum of Dirac. Whereas after taking the limit, I can solve the equation using this initial condition, the nice one which is there. Okay? And of course, it also means that, that Fm t converge pointwise this time to an Ft, which is just the C phi and then this d mu t, which is the limit that I've written there. Right? So this means that if I think about at the mean field level, right, which is taking this limit where you take the width to infinity, you can essentially, forget about the m in this equation. Forget about the m, change the initial condition. Right. So now let's think a little bit what this equation tells us. Right? So this guy here, these equations, are just a gradient flow over this energy. This is also a gradient flow, but in a different metric. So the fact that you had gradient level of the particles here, or the parameters, induce a gradient flow at the level of the measure. This was in fact true even before taking the limit, right? But this gradient has a metric that has changed. So let me write it. So you can guess what it should be. Is what you have is, I'm going to write the equation for ut in a slightly different way, which is I'll write it as being dc. Okay, so there's two terms. This term so I can write it like this, provided I introduce, allow me to, I'm going to erase this guy here, the initial condition, where I have introduced an energy, which is just a functional of mu, which is in fact simply this loss, but viewed as a function of the measure rather than the parameters. So let's write it. It's just this. So this means, if you want to show that these two lines are the same, right? You just need to use the fact that dE over d mu is so it's the integral of c phi theta d mu minus f star scalar product phi theta, like this in H. Right? That's what the functional derivative tells you. This is f, which is the one that I was writing here. And if you take now d over dc, you'll kill this guy and you're going to get this term. And if you take d over d theta, you'll get the gradient over d theta and you'll get that term. Right? So you can think about the equation like this. Okay? So if you think about this for a minute, you're first very happy, and then we will have to temper a bit the enthusiasm, and then we're going to be happy again, you'll see, which is that if you look at the equation, you say, it's a gradient flow on a convex energy. In fact, it's more than convex, it's quadratic in mu. So it looks like all is well. Right? If you were to think finite dimensional.
You miss a sign or somewhere, so it seemed that you'd want to go down in energy, right?
But this, so there's this metric, right? Okay, okay. There's no sign. The sign is correct. I'll show that to you in a minute. Okay, so so you are indeed going down in energy and on a convex landscape by gradient descent, but unfortunately, you see that the metric has changed because there is this dc mu dc and d theta mu d theta that have appeared. There's this operator that has appeared, right? And that's the one that this is gradient descent in W2. This is GD in W2. In other words, if you were to think discrete time, the derivation here would not arise, but you could think about this as the continuous time limit of a proximal scheme where the Bergman divergence that you would use is W2, and you do steps that decrease this energy. Wasserstein 2. Okay? For the rest, I want to discuss. This is not very important, so allow me to not go in there. But the difficulty that we now need to face, and I'll first explain it to you in word, and then we're going to see that in formula, is that even though this is a gradient descent on a quadratic energy, it may not reach the minimum. And that may look bizarre at first sight, but the problem is that the speed at which the measure is evolving on the energy depends on the measure itself. And if it becomes too sparse, I could imagine that I start with an initial condition where my measure has mass everywhere. It has a density and is strictly positive. Okay? Even if that's the case, it could be that the mass starts to be smaller and smaller in certain regions, and that stops the evolution. This phenomenon is fairly well known to physicists in the sense that, this is not the case here, but you could imagine that if you're evolving interacting particle on a double well landscape, you could have that some of the particles go in one well and some of the other, and they never manage to equilibrate between the wells, even though the minimizer in that case would still be that you put all the particles in the deepest well. Okay? So let me try to, there's a difficulty with this equation, and I'll try now to illustrate what the difficulty is in formula and show you that that's why we bothered to put this C all along, that in fact there is no difficulty. So bear with me, I'll kind of.
Could you repeat again what gradient descent equation was this?
This is gradient descent in Wasserstein metric. Okay?
Of the energy E.
Of the energy E. Okay. So this little calculation is for boys, which is, suppose I look, how do you prove convergence, right? Let's look at the way the energy varies, right? So then if you want to do that, right, what you do is that you use chain rule, which is you say, well, that's the dE over d mu times dt. Well,
So in some sense, I can understand now why it's descending, because you want to put more measure where you got more errors. In some sense, you want to increase in the measure space. If you had if theta contributed a lot to the energy, you want to actually put more measures.
yes,
there, so you do
yes.
it.
But this little calculation there will show you also we go down. So this is chain rule again. Okay, using chain rule in functional derivatives. Now you use the equation for dt mu, right? And you integrate by part in C and in theta. And what do you end up having is simply this. So did Andrea do this calculation or no? Did someone do this calculation? Nobody? Okay, this is the d mu t, and now I have my minus. Because since I had the plus here, when I integrate by part, I change the sign and I get that, right? So this is clearly less or equal than 0, which is indicating that the energy is decreasing. Yes? Okay. The problem is that if you look at this equation and you ask what are the stationary points of this equation, the stationary point of this equation simply tell you, you will stop when this guy is equal to 0 on the support of mu. This is the condition that you get there. That's a fixed point. You cannot reach anything else than that. But that's what you reach, right? But you need to distinguish that with the equation for what does the minimizer of this energy satisfy, right? And that's, okay, so this is a little bit of a complicated calculation. So it's a quadratic energy, so I can just look at the first variation because it's convex and 0 the first variation. But the way you need to do the first variation here is a little bit more complicated than the standard one because you're taking variation with respect to measures. And these are probability measure. In particular, if the measure is equal to 0, you can only do variation in one direction because you cannot put negative mass. Okay? So I'm not going to do that, but if you do the calculation, what you end up having is this condition needs to be satisfied. Actually, I just wrote it wrong. You need to have that, you end up having that. This condition, this is the condition for the minimizer. They need to satisfy this with equality on the support of mu. So, does anyone has seen these guys?
Is this like the Maxwell construction or not?
You mean as in for phase transitions? No, the way you arrive at these equations is actually kind of simple. You just take first variation of this object, but you simply remember that you don't, what happened is that if mu is equal to 0, the term in d mu is positive, right? And so the factor that's in front of the delta mu, the variation, doesn't need to be 0, it just needs to have the right sign so that it pushes you up. Yes? It's because it's like you're taking variation at the boundary of the set. You can only go one way. Okay? You get these equations. They are standard. Like if you have not seen that, I can give you reference. Does the explanation that I just give makes any sense or not? Like
I got lost what that means. But I understand that bracket needs to be 0 for the dynamics to stop. How is that related to what you're saying?
So, okay. This is the equation that you get. The dynamics that you obtain here tells you that if you do this gradient descent, so which is essentially equivalent of doing, this, what happened at this level if you have sufficiently many particles, what you will end up having is that the energy goes down and will reach a critical point or stationary point, which is such that this bracket here needs to be equal to 0 on the support of mu. Either mu is equal to 0 or this is equal to 0, then you stop because then you get d over dt of E equals 0. So the energy goes down until this condition is satisfied. Now you ask yourself, does that guarantee that when there's no convergence rate, it's just a matter of converging, does that guarantee that if I stop, I'll stop at the minimum of at the minimizer of the energy? And unfortunately, the answer is a priori no, because the condition for the minimizer of the energy are these conditions. Okay? Not these. Now, does that make sense? No? Right? So these conditions are obtained, right? If you were to do standard variation, you would simply have said the condition is dE over d mu is equal to 0. But the situation is a little bit more complicated here because there's a measure, and measure can, if you end up having something where the minimizer has no mass in certain places, it's just the variation can only, the delta mu, the variation needs to be positive at that point, so you get these equations. Okay?
Can we think of this being different also than the mu equals 0 because the mu is a density and it has to be conserved as well, like it has to integrate to 1?
Yeah, that's right. There's this condition and the fact that the measure needs to always remain positive. So you have these two conditions. But now you realize, and maybe, once again, it seems that maybe I should give all the lecture twice so that the second time is a bit, I know whether I should skip or not skip. You realize that because of the structure of the energy, because of the structure of the energy that we have here, in fact, meaning because of the C that we have introduced, in fact, in all cases, these conditions are the same. So let me explain that. First of all, okay, so maybe before I go that, what is the difference between this and this? Right? This tells you that, this says that on the support of mu, this functional derivative, which is a function of theta and c, needs to be constant. Right? That's because this is an integral. So this guy here, this object here is a function of c and theta. This is an integral. So this says that on the support of mu, the energy needs to be constant. The variation, the grain of the energy with respect to mu needs to be constant. This says almost the same thing, except that if the support of mu is disconnected, right? If you have, if mu has a little bit of mass here and then it has mass here, but it's strictly, this is mu, and it's 0 strictly here, this one tells you that you can have one constant here and another constant there. Whereas this guy tells you the two constants needs to be the same. For physicists, it's exactly what I said before, which is that if you have interacting particles in a double well, for example, right, you could have that they get trapped into the well and stuck there, even though the global minimum would be to put them all in the deepest well. That's that. This is getting stuck with the wrong mass in the well, and it should be a common mass with respect to what's here. Okay? Now, what you realize, however, is that the condition here makes that. So when you look at what is actually happening here, you realize that the conditions are satisfied because you see that this condition, I can write it explicitly, right? What this guy is C times, there's a C there that I can take out, times this integral, so maybe I could put C prime to not confuse you. This is an integral, so this is a constant in that minus F star, right, that you multiply by phi theta. This is the condition that you need. This guy is just this. I've just rewritten it, right? But you see that since C can be positive and negative, right, the only way you're going to satisfy these two conditions is essentially, forget about the C, is if this is equal to 0 and the support of mu, right? It has to be like that, because otherwise, I can, without changing anything else, I can just vary with the C and change my sign. Okay? And this condition here is implied by this one, which is that if you just look by this one, this guy here, the fact that the sum here needs to be equal to 0, so this one needs to be equal to 0, but this is just telling you that the square of this needs to be equal to 0, which is the same. Okay? So let me maybe try to explain a little bit what has been going on here, because I realized that maybe I introduced you a difficulty that you didn't know about, and then I told you, in fact, this difficulty doesn't arise. But I mean, so is life. I think, right? So what happened here at the end of the day is that even though I wrote this energy as an energy on a measure, you see that in fact it's not an energy on a probability measure, because it only depends at the end of the day of what's happening on the radon measure. And radon measure I can optimize as regular function in a way. There is no sign condition or normalization, and in fact that's what plays the role that's there. You can think about that in a different way, if you wish. Again, if you're a physicist, I'm trying to give you an image, which is that you can think about this as really as parameters, right? And these guys are charges of the parameters. And then it looks a little bit like you will have, particle with a charge, where you can see, if you look at, this is the interaction potential that you have. The charge there, the value of the charge tells you whether this particle attract or repel. Now in standard particle system in physics, charges are fixed. And so either particle all collapse together or they repel. But in this case, the charges themselves are evolving. And so that's the way, in fact, they can escape. What looks like a local maximum can become a local minimum just by changing the charges. And so that's why they can actually visit everywhere, and that you have, right? And I gave you here an argument which is a little bit, if you want to make this rigorous, it's a bit more complicated. This argument is the one we gave in the paper with Grant, but there is a paper by Shiza and Bach where they prove rigorously that if you have this structure with this C here, then the dynamics reaches the global minimum. Okay? So you zero the loss at the end. Well, or this energy, if you wish. Okay? Okay, so now you can do better than this, and I'm not going to do it here, which is that if you initialize, so now we need to think about the fact that in practice, of course, we are not evolving these measures. We are stuck with this. Right? That's the dynamics that we would do in the computer, or even a discretized version in time of that. Right? So one interesting question is to ask, what's the error that I'm making at finite m? So you know the error at initialization because that's just CLT. If you draw the initial condition independently from a given measure, right, you know that initially the error that you will do will be controlled by the central limit term. Just that's the calculation I did at the beginning of the class. Right? What's not completely clear is what happened dynamically. Because these particles that were independent at initialization now are evolving, in a way which is coupled through these. But so these results here, this mean field limit, is what we call also propagation of chaos, guarantees in fact that these particles remain very weakly correlated all along the evolution, and they satisfy a dynamical CLT. So in other words, you can write down a dynamical equation not only for the measure, the limit, but if you wish for the difference between the two. Okay? Scaled by square root of m. And you can analyze its dynamics for all time in certain cases and then prove that the error remains controlled at all times, that you remain in the CLT regime for all times. In practice, what does that tell you? It tells you that the statement that I'm making here at the level of the measure in the infinite with limit is something that you can approach in practice by doing this dynamics at finite m. Okay? Okay. Now I have, how much time do I have? 10 minutes? 15 minutes? 15.
That's a good question.
There were two questions. Yeah, go ahead.
Okay, in terms of what you said earlier, then wouldn't it be more transparent if you're able to write a dynamical equation for the random measure instead of the mu-t?
So that's a very good question. The way I've done it here, you can't. Because if you multiply this by c and try to integrate over c, you see that you're going to get a dc. So if you do it, you'll see that the equation doesn't close. Okay? But Lenaik, Shiza, notice the following thing, and that's related to what Bart was saying. I could change the metric here. Okay? And I could do the following thing. I don't want to discuss that too much, but you could add a ci here and divide by ci there. Right. And then it's like this conic metric. This now means that the c cannot change sign anymore. They are all positive, so you would have to have if you have a function that, if your target is positive and negative, you need to assign a budget for the part that you want to represent as positive and the part as negative. If it's all positive, it would work with just positive charges. If you do that, you can actually write down an equation that is closed for gamma, the radion measure, and it's unbalanced transport. And that's in a paper of Chiza. But I'm not going to do that. So this is what you would do if you don't play with this metric. Okay? Now what I want to discuss in the last 15 minutes is the connection, because it may look very obscure at this point, but in fact this is closely connected to the NTK. And in order to do that, I just want to do one more little calculation. So I wrote for you here the equation which is the evolution equation for the measure. It's written there. Let's focus, just look at this. It's here. Okay? Now, you could ask yourself, can I use this equation to actually write an equation for f? At the end of the day, I don't really care about the measure. What I care about is the output, right? Or the output, or this is what I'm learning at the end of the day. This is the output of my neural network, right? Or my model, more generally. So, can I write down an equation for this guy? So what would you do if you do that? Well, I can take the equation which is here, multiplied by C, there's a theta missing here, multiplied by that, integrating over C and phi, and, you know, looking at the result. So I'm going to write down the result, and we'll see if you agree with it. It's, what you get as an equation is this. It's an equation that I can write like down. Where this is, so maybe I can write it down explicitly in, you know, by using x if we use the norm. So it's something which is like, bear with me just a second. Because this is an equation that you will recognize. So the equation that you get is this. If you use this is in the population loss. If you were to use the empirical distribution, you would need to replace this expectation here just as a sum over the data set. Okay? And the m that's there, this m, the m of mu t, the m of mu, evaluated at mu t, is just the fact, you see that when you replace you multiply that by phi here, right? You can see phi and then you integrate by part. What you end up having is this guy. Is this object integrated over d mu. So this is mu t and this is mu t. Okay? So in the paper with Grant, we wrote this equation, right? It's useful to look at it, but you need to remember that it's not closed. And the reason why it's not closed is because there is this guy here. The measure that's appearing here, right, this guy, is evolving. So in fact, I need, you know, somehow I would need to know how the measure is evolving to know how this kernel here is evolving. Right? So it's not closed. Okay? But you can learn a few things from it. For example, you know, this kernel is obviously positive definite. Right? It's just only squares. Right? And again, so that means that this is also a gradient descent, if you wish, in a strange metric. Right? Just that it's actually evolving because of the mu t. Okay? Which again could lead to problem. You know, this guy for all finite time is in fact strictly positive, so it's positive definite, but it could be that as t goes to infinity, it could become only positive semi-definite, which would mean that you don't converge. That's the problem that we have discussed before and that we have already kind of avoided in a way. Okay, said it doesn't happen. But this is the place where I can now try to explain what's going on with the NTK, right? Because you know this kernel is in fact the NTK kernel, except, so this, I think it was denoted by a capital theta, right? This should, these are the notation we use in our paper, but this is what was denoted in yesterday's lecture by capital theta. So let me try to explain what's the connection with the NTK, okay? So let's do that, you know, the last couple of minutes. I wanted to discuss about generalization, which in fact is perhaps the most important question, but I think I will have to skip that. It will be in, you know, in the note. So you remember that I said at the beginning, let's look at this. Right? Now, this 1 over m is what you need to take to be in the law of large number regime. It's an empirical expectation. Yes? But I could ask myself, well, in the NTK, I could try to replace, let's imagine I take another scaling. You will see at the end of the day, I put the square root here to be really in what's called the NTK scaling, but in fact, you could take any m here, m which is 1 minus alpha with alpha, so that this is less than 1. So 1 minus alpha less than 1 in this range. Okay? Let's forget about that. Let's just take that. So if you do this, just this, as m goes to infinity, this doesn't have a limit, right? There's no law of large number. In order to get a limit here, you need to have a centering condition and you need to use the CLT. Okay? That's a question that has been alluded in the previous lecture, which is, what do you do with the initialization? Okay. But there's a way to get rid of that, which is just, okay, let's imagine that so now the zeros here will always be, I'm going to think about this model where these guys, the Ci and the theta I here, are the initial condition that I was talking about before. And as you can, so these are taken from a certain new zero, right? And I will assume, and they are, let's imagine that they are independent. Okay? So, and I'm going to use a representation. So instead of using the Fm we have been playing with before, we were playing with this Fm, which was 1 over m, the sum from I equal 1 up to m of Ci phi theta I. I want to play with this Fm. So I'll take it Fm NTK, let's say, like that, right? And now you ask yourself, what can happen to the Ci? So I'm going to do an argument which is very heuristic, and if you want to make it rigorous, well, then you need to go to the paper of, the many papers that have been written on that. But what do you need to do here? In which case will you have that this function, so initially, if I think about this function is 0 at time t equals 0. If I think about these guys, so I'm going to evolve everything in time, so I'm going to think about that as the time evolved parameters by gradient descent from these parameters. So by definition, initially it's equal to 0. But I can ask myself, how can they move? And I would still get that this function has a well-defined limit. There's only one way this can happen, is by going back into the mean field, and that's to appeal to the law of large number, is to say that whatever will happen will require that this is satisfied. Plus a little O of 1 over square root of m. I'm going to be a little bit sloppy here. And theta I is a theta I 0 plus 1 over square root of m times theta tilde I plus. So what does that mean? That means that in the NTK, in the scaling of the NTK, the only thing that can happen, if you want that, that you decrease the energy and the loss, and that you remain with a function representation that has a limit, is that this guy can only move O over square root of m away from the initial condition. Okay? If you take 1 over alpha, you would keep the alpha there so that you get 1 over m. Okay? So this is true for any, but let's just discuss that. So what happens if you do this? Well, if you do this, so maybe I can write it here. The tilde, so I'm just saying, so the tilde are the discrepancy. So you can think about it in two ways. This is what's going to happen. Dynamically, this will be happening. But before even I think about dynamics, if I just think about function representation and I ask myself, what can happen to this object? How much can I vary these guys away from Ci 0 so that I have a limit? I can only do this. With Ci tilde and theta I tilde that are O1, right? That's the idea. So if you do that, you see that, well, I can write it like here, right? What you end up having is that, well, you just do Taylor expansion, and what you get is 1 over m, the sum from I equal 1 up to m of what? Well, Ci tilde times phi plus Ci 0 theta I tilde d theta I the phi at theta I 0. And then, there's a correction here, which is a little O of m. So that's the function representation that I obtain. And now you can ask, so you can ask what is happening now at this level if I think about the dynamic. You could do it differently, which is you could simply write down the gradient descent at this level. This is more like the way also in a paper by Bach and Shiza they do it, and ask yourself by how much do they move. But the intuition is just this. at the end of the day, this is the scaling I need to have in order that if I take now m going to infinity, I'm going to get something where I have, c tilde phi theta 0 plus c0 theta tilde times d theta phi theta 0, right? And then there will be there's two measures that I need to introduce. The d mu, which is on tilde, okay, so d mu tilde theta tilde, I wrote it the other way, this guy. And then the d mu 0, which is on the c0 and the theta 0. In general, this guy is conditional on this one, but since I'm going to optimize them, it doesn't matter. You can consider them to be independent. And what is happening now is that this guy is fixed. This is your initialization. This is the initialization that you have taken, and this is the one that will evolve. And so now you can actually redo all the mean field calculation that I just explained to you in this representation, where what you think about evolving is this measure, or correspondingly the parameters that are these. And you can do what's the function representation, what's the dynamics, and so on and so forth. You realize that what you're doing here, because these parameters are fixed, is in general, certainly if the Ci0 were equal to 0, imagine that the Ci0 is equal to 0, this is it's a smaller space than the one that you do with feature learning. Why? Because you only allow the weights to vary, but no longer the features, if you want to call them this way. Okay? The statement is a little bit more complicated in this representation because it's a bigger space, because these guys can vary too. But in general, you can show that this guy is a smaller space than the Banach space I started from, because it's a linearization of it, in a way, around a fixed. Okay? Whether this linearization, it's not a judgment here, right? Whether this linearization is sufficient or not, I'm just stating, the fact. So that a priori could be, a bit of an issue. But what you gain is that if you now crank the machine and you redo exactly the same calculation, the one that I did, starting from this, what you end up having is that, and I'm just going to write it, is that you go back to, if you think about what happened in the NTK, you get exactly the same thing, but with one important difference, is that this becomes mu0. Just do it like it's, so it's the same kernel, but what you end up having is that instead of having this nonlinear evolution where f evolved by a kernel that adapts itself through the equation for mu that I've written there, no, it doesn't adapt anymore. The mu is fixed. But the kernel is exactly the one that I wrote over there. It's just that you have frozen it by changing the scaling. Okay? So, I don't know, this is like I don't want to give you, of course this, what I'm presenting here is just my intuition on how to understand the NTK from the perspective that I, gave you before, and I think it's useful. Of course, the advantage that we have seen, in all the lectures this week is that once you work with the NTK, your life becomes much easier because you know what this kernel is, right? Since you know what your network is, the phi, and you initialize it. And so you can do all of these, interesting analysis, right? It's much harder if you want to do it at this level since, the kernel is itself evolving. But my feeling is that it would be worthwhile to try to push a little bit into that direction and to try to understand what happened with these dynamics if you go into what's called feature learning, because at the end of the day we know that at least certain part of networks do evolve, which is corresponding to that. Okay, and I'm out of time, so I'll stop. I just want to mention one thing at the end, which is going back to these dynamics, right? The framework, so this is, as I say, is more like a roadmap because it's a very loose framework, in fact, that they've explained. But this framework also allows you to understand generalization. Because if you understand, in order to understand generalization, you can try to understand what is going on, not anymore at the level of the parameters, but again, looking in measure space. Okay? And there's a lot you can say, in but it's quite incomplete and unsatisfactory. For example, the norm that I introduced at the beginning, it was here somewhere, that's why I point over there, it's not there anymore. This TV norm, in particular, can be used to bound the generalization error, which is, how good, what is the value? Imagine that the population loss on its minimum is 0. But now I evaluate the population loss on a minimizer of the empirical loss. What will be its value? How bad will it be? Okay? You can control that by the norm, by thinking about it in this mean field limit, you can control that by the norm that I introduced at the beginning, this TV norm. Okay? Which, at the end, if you want to summarize it all, says, because this is like the last word, it says, don't worry about overparametrizing. Don't worry about the width of your network. It's an old statement, I think Bartlett already said. Don't worry about the width. Overparameterize as much as you want, but control the weights. And then you'll be fine. Okay? And no, I'm really done. As I said, just reiterating one more time, many of the things that I've told you here were non-rigorous and requires a lot of work, especially because I didn't assume that this was a shallow neural network and that this is a real unit. This can be any model. This in itself could be a deep neural network, right? So there's a lot of analysis that can be done or should be done with that, but I think that's a very promising avenue of research for, the future generation. That's you. Okay.